Hello, I'm Dawson, and today will be presenting a movie recommender system using deep learning models. Here's the roadmap. I'll start with the problem statements and project objectives. Then I'll cover the data collections. After that, I'll be explaining the baseline model and then moving on to more advanced deep learning architectures, and then including neural matrix factorization and lights GCM with a hybrid loss. Then I'll show the performance I've obtained and conclude with recommendations. So let's start with problem statements. So the core issues are mainly content overload, where streaming platforms often give out top 10 or popularity-based lists that ignores individual preferences. This actually leads to users' low engagement and churn. And secondly, there's generic recommendations, where streaming platforms have thousands of movies and TV series, where users struggles to find title that matches their taste. Thirdly, there's cold start users, where new users have rated very few or no movies. This actually make them hard to infer their preferences without any initial signals. Lastly, there's sports data for niche movies, where less popular or recently added movies have received very few ratings. This made the collaborative filtering method struggle to recommend these movies accurately. So let's move on to project objectives. So our objective is to make a hybrid deep learning movie recommender system which uses compact user and item embedding and also uses site information such as genres and demographics. And it also uses nonlinear interaction modeling. So with this model, we hope we can resolve choice overload, surface titles each user will actually enjoy, and reduce the time for them to endlessly browsing. We also want the models to learn from limited feedbacks so they will adapt quickly when a user only has a rate of rated a handful of movies, and also adapt quickly when a new movie are added. Lastly, we also wanted the model to personalize effectively, so it would balance long-term taste profile with recent user behavior and combine collaborative signals, which is our similar user signals, with content signals like genre and cast. So now let's move on to data collections. So the source of the data is actually from Group Lens Research Project and University of Minnesota. So the structures of the data is actually with three files. First of all, rating.dat, which contains 100,209 user movie interactions with timestamps. There's also user.dat, containing 6,040 users' demographics information such as age and gender. Lastly, there's movies.dat, containing 3,952 movies metadata, such as genre and year of release. So let's look a bit into the exploratory data analysis. So for figure 1.1, we can see that with an over 57.7% 4 and 5-star rating indicating rightly skewed positive feedbacks, and this helps us knowing that most rating clustered at top, and we can decide the relevancy threshold of greater and equal to 4 while computing ranking metrics like precisions at 10 and recall at 10. From figure 1.2, we can also see long tail distributions. From the distributions of rating per user, this actually indicated a, extreme sparsity, and this might actually suggest that we have to implement a strong user bias regulations to avoid overfitting. Now that I've covered our data collection, let's move on to our baseline model, which is the matrix factorization. I've converted original. Let's go on to the data preprocessing part, where I've converted original user ID and mover ID into serial-based continuous indices. Since our matrix factorizations and baseline modeling and future neural networks model will require integer indices, and this conversion also compacted the index space for more efficient lookup and sparse matrix factorizations. Then we also did encoding side features such as genres and gender, which we use as one hot and multi-hot encoding. Lastly, we also split the data into 60%, 20%, and 20% into validation, test set, and training set. So now let's move on to the model architectures. So on top, we can see the formula for our baseline model, which is the matrix factorizations. It is a standard matrix factorization with user item latent factors and predictions combine a dot product of embedding with user bias, item bias, and a global offset. And finally, outputting our predictions. So now that we're done with model architectures, we actually did hyperparameter tuning as well, where we did a grid search on validation sets with 100 epochs and 4 patients. So we did a hyperparameter tuning spanning from latent factors, where we use from number 10 to 100, We also did a regularization rate, learning rate, and maximum iterations. And the best combo have been highlighted into orange, where you can see it's 10, 0.05, 0.001, and 20. So as for our model fitting step, we've started off with a training set where we fit the matrix factorization for each hyperparameter combo. Then we use validation set to pick the best hyperparameter combo. Then we combine the training and validation set to retrain for the final model. And then we use this test set to evaluate on the final model's performance. So now let's move on to the model's performance. So we actually have five metrics on measuring our performance for matrix factorization. First of all is the RMSE, where it measured the average square difference between true and predicted ratings. And our result is 1.2305, which is actually meaning that we're only 1.2 stars away from the true ratings. Then there's the MAE, which measures the average absolute differences between true and predicted ratings. And matrix factorizations actually resulted in 1.0018 stars away from the true rating on average. Then let's move on to the precision at 10. It actually measures level relevancy of top 10 movies recommended to each users, which are actually larger than or equal to 4-star ratings. And there are 56.5% of the movies recommended are relevant. Then we move on to recall at 10. The capture rate from all the movies a user has rated more than or equal to 4 stars ratings. And from our model result, 55.85% of these movies are captured. Lastly, there's NTCG at 10, that combines relevance and ranking positions. Then we normalize by the best possible ordering. And the result of the model is 0.7013. This means that it gives 70% of an ideal ranking possible. Now that we're done with baseline modeling, we're going to move on to neural network matrix factorizations. And now we can look at the model architectures. So it has two branches. So first of all, a generalized matrix factorization branch and a multi-layer perceptron branch. So user and items ID are embedded separately, flattened and combine anonymized multiplications for the GMF and a deep dense tower for the MLP. The outputs are concatenated passed through a linear layer and augmented with user and item bias plus the global mean to produce the final predictions. So now we're done with the model architectures. So we also perform hyperparameter tuning as well with using Greek search, also using 100 epochs. But this time, besides using latent factors, regularization rates, and learning rates, we actually did a MLP layers depth and width as well on hyperparameter tuning, and we also highlighted the best combo in orange as well. As for the model fitting steps, it's the same for matrix factorizations. So it's just training steps and training set that fit neural matrix factorization for each hyperparameter combo. Then we go to validation set that pick the best hyperparameter combo. After that, we do the training and validation sets and we train for the final neural network matrix factorizations and use this test set to evaluate the final performance. And the model result is as follows. And we can from all the metrics we use, we can see that there's significant improvements from RMSD, MAE, precision at 10, recall 10, and DCG at 10, which all of them showed a significant improvement as well. So now that we're done with neural network matrix factorization, we move to a more advanced neural network, which is like GCM with hybrid BPR and MSE. So we did a further data preprocessing where we concatenate site features, so it prepares fused site information embeddings. We also build a symmetric biparty adjacency, so it prepares the light GCM propagation matrix. We also did hard negative candidate pool that provide negative for BPR style lots. And lastly, we did tensor conversions, which we convert all index and rating arrays into TF constants, where tensors for efficient TensorFlow computations. So this is the model architectures where we use the side feature fusion and hybrid loss. Like GCM propagates embeddings over user item graph for a specific number of hops. The outputs from each hops are combined with learned softmax weights, site informations, user features, and item features are passed through a small MLPs and fused additively. Prediction incorporate dot products of a final user and item embedding plus biases and the global mean. The loss is a hybrid of ranking-based PPR regression MSE controlled by a mixing parameter alpha. We also performed a semi-hard negative mining to choose challenging negative each at each epoch. So, for light GCM with hybrid PPI and MSE, we did the same hyperparameter tuning, but this time we used number of propagation layers, embedding size, regularization rates, and learning rates. So for the model fitting steps, we did the same for training set, where we fit light GCM for each hyperparameter combos, validation set where we pick the best hyperparameter combo, and the training validation set where we train final light GCM and using the test set to evaluate final model's performance. And for the model result, we can see that similar to the neural network matrix factorizations, it actually gives out a very significant improvement on RMSE, MAE precisions, recall, and NDCJ as well, giving a more relevant and ranking top most related movie list for users as well. So let's talk about our preliminary results. So from the model results, we can see that RMSE, MAE are giving significant improvements from 1.2 to 0.9, meaning that from our true ratings and predicted ratings, there are smaller gaps now. As for precision at 10 and recall at 10, even though it does not seem like there is a big change shift, but like it actually signifies there is a big improvement on relevancies that are recommended to users. And recall at 10 also signify that 65% of the movies are recommended are within the user's top 10 movies as well. As for NTCJ at 10, we can see that from a baseline model, only 70% of the list is an ideal ranking. But now that we're using like GCM, we can see that 87% of the movie list is actually an ideal movie list already. So based on this finding, key recommendations are expand the hyperparameters to search to include deeper publications so that we can include multiple layers. And we also want to schedule for learning rate and hybrid mixing parameters, advance semi-hard mining to a dynamic difficulty adaptations. We also want to shift to a mini batch training with per batch negative sampling for scalability, and perform a systematic ablations to quantify the contributions of side features, biases, and each loss components. Even though most of the metrics are improved significantly, especially RMSE, yet it remains high because core training emphasizes relative ordering via BPR, only partially correct scale and fine tunings, and this number indicated model captures relevancy to a degree, but there's a gap in absolute rating accuracy and room to sharpen top K quality. So this is my reference list, and thank you.